This conference will now be recorded.
Right, so this presentation, this lunchtime, is about track buckling resistance and the maintainer, and it's really written from a point of view of what you need to consider if you're maintaining the track, but we will cover the subject quite widely. And it's also a bit of a look at how we got where we were today, the standards that we have around stress management and track maintenance were born out of some quite serious incidents in the past. So what are we going to look at? If I can move on. That's it. So what we'll be looking at, so the presentation looks at some of the principles behind how track resists buckling and explores the role of the maintainer in managing these. And it looks at some key learning from past track buckles and how this has been used to develop the standards and procedures we use today. And it's worth noting we're going to talk mainly about CWR, but we will look at some of the issues around jointed track as well. So from the 1900s, the application of the science of thermodynamics was producing more powerful locomotives capable of hauling heavier trains at higher speeds. Improvements in rolling stock had increased train weights, but lowered rolling resistance and improved wire quality made them more comfortable at higher speeds. And of course, even by the 1930s, the competition from air travel over longer distance was seen as a real threat to the railway. And the diagram on the left here, the starting point is Stephenson's rocket down in the corner here. And the other end of the scale is where we were in 1946. Okay, so what were the drivers for moving away from jointed track? Well, increasing train speeds and weights, the need to improve ride quality, particularly after World War II, the need to reduce maintenance costs as labour costs had soared during the wartime years. And benefits included obviously the elimination of all the failure modes associated with bolted joints. And of course for the operating side, it's improved fuel economy. So the lines on the chart on the left, the black line shows the power output increase. The total weight of locomotives is in black, yeah, and the boiler pressure is the vertical shaded line. So, and of interest on the right is some proposed locomotives that the French railways were already talking about in 1945, and the locomotive shown number 1 on that list is a 464 designed to haul a 650-ton passenger train at speeds of 140 kilometers per hour, upper 1 in 200 gradient. So already then we're talking about big trains running at relatively high speeds.
Andy, is it possible to show your presentation full screen? We've had a request.
It's a full screen on mine, but hang on a minute. Right, I'll have to go out of it and come back in again, I think.
Just drag it up yourself, your screen. People can just drag your screen up themselves to get rid of everybody's names.
Yeah, I can do that. Did everybody hear that? If you want to increase it, just drag your own screen up, please. Thank you.
Right, okay, let's carry on. Right, so whilst there are obviously, as we've said, benefits in moving away from jointed track. So we talked about reduced maintenance costs and the removal of rail end failure. There were, of course, inherent risks. So this was a new form of track which was not fully understood as against jointed track, where we had by then over 100 years of experience. And the big question was, how do you manage track buckling risk when the expansion joints are removed? So introduction started in the late 50s in the UK. And British Railways were comparatively late starters and about 20 years behind continental Europe and the USA. And to understand this new track form, like many other railway administrations, British Railway started on a basic research on the stability of long welded rails. And of interest, the top picture is installing long welded rail in 1957 at Langworth on the Western using panel bows. And the bottom picture is de-stressing, as it was then called, using heaters. And we'll talk more about that later. So what was the experimental work involved? So the research work involved laboratory testing of different rail fastening systems and buckling of track under controlled conditions, which are the two pictures on the right. So the top picture is the thing all set up. And you notice down the forefoot, there's a series of heaters, which are warming the rail up, yeah, and down what would be the other side of the rail as well. And then the lower picture is the track after it's buckled. Notice there that it's quite an explosive event. It's tipped everything over as well. They also set up site measurement of ballast resistance and extended measuring of rail movement in 3 dimensions of track in service throughout a full year to see what effect heat, what effect trains and things were having. And they published the results in 1961 in a report entitled Experiments on the Stability of Long Welded Rails. It was a research document intended for sharing experience and knowledge with other railway research establishments. But it was the starting point, and it's the starting point of my talk today. So in case many of you probably won't have seen a track buckle, this should. So this is the track buckle actually happening. I'll run that again because it was very quick. So again, that's a buckle produced under controlled conditions, and it's worth stressing here, you can see what the big risk with a track buckle. So compared to a broken rail, a buckle is a much more serious issue. What would tend to happen is if a train attempts to negotiate this, even at comparatively low speed, it'll enter the first curve okay, but when it comes to this sharp reverse, you generally get a flange climbing derailment. Which is not good news, particularly as buckles tend to happen under trains or immediately after trains have passed. Right, so one of the things that came out of the report was this equation. So they demonstrated that for any track, the compressive force P required to overcome lateral resistance was as per the equation shown. But don't panic, I'm not going to be testing you that today. The form of the equation isn't particularly important for today, but the key thing is that it shows the inherent resisting of track to buckling comes from 3 factors. So the first term is on the left there, comes from the contribution of the rails to resistance to buckling. So obviously from a maintenance point of view, there isn't anything you can do to increase the resistance, as it's dependent on the properties of the rails used, and in general is not something that's changed in the course of maintenance. But it is worth remembering that developments in track engineering have seen introduction of heavier, stiffer rail sections, moving from the 95-pound bullhead and lighter bullhead sections through 98-pound flat bottom up to the current CEN 56 rail, and of course we're also putting in CEN 60 rail on our highest category tracks. So another point to remember as well is thinking about the issue is we have quite a number of buckles in S&C on the main line, and a lot are associated with full depth switches. So that's the one, the diagram at the top. You can see that to create the switch, we have to machine quite a large part of the foot of the stock rail away. And obviously this reduces quite considerably its ability to resist bending. So in full depth switches, as I said, we machine the foot away to allow the switch rail to close against the stock rail. And experience shown that this type of S&C is vulnerable to buckling. And and it's something to bear in mind if you've got stressed full depth switches. The second term represents the contribution of the sleeper fastening combination to the resistance against track buckling. So here a reduction in the sleeper spacing D and/or an increase of the fastening coefficient C would cause an increase in the overall resistance to buckling. And I think that's quite intuitive, that the stiffer the joints between the sleeper and the rail, and the more of them there are, then the stiffer becomes the track acting as a beam in its totality. So again, from a point of view of maintenance, really important to remember that keeping the pads and insulators, rail fastenings in good condition all contribute towards resisting buckling. The third term represents the contribution from the ballast sleeper interaction. So if W equals the ballast resistance per sleeper and D equals the sleeper spacing, then this demonstrates that reducing the sleeper spacing causes a corresponding increase in the overall term and hence an increase in the resistance to buckling. And again, I think it's fairly intuitive. If we use more sleepers or sleepers that have a higher resistance to moving in the ballast, it will improve buckling resistance. So how does the sleeper actually build up its resistance? And this is probably one of the most important things. And again, it's an area where maintenance can have a particularly big effect on it. So bottom friction, this is the resistance at the base of the sleeper and depends upon the friction between the ballast and the bottom, sleeper bottom, and therefore on the frictional value and the vertical load applied. Clearly, if there is voiding, this resistance is compromised, but it will be increased both by using heavier sleepers and rail and also by closing up the sleeper spacing. Bottom friction is reduced by between 20 and 40% by the lift-off wave of a rolling train, which is why buckles may be triggered under a train or immediately after a train has passed. And you can see that accounts for some 45 to 50% of the total resistance. The sleeper end resistance is the resistance from the ballast shoulder. It only becomes effective as the sleeper actually starts to move. So it's similar to passive soil pressure in that respect. It depends not only on the height of the shoulder, the ballast density and its level of compaction, but also on the distance covered by the sleeper. And sometimes when a track has approached buckling, you can find a small gap at the end of the sleeper where the lateral resistance limit has been approached. Clearly, a weak or deficient ballast shoulder will not provide the optimum lateral resistance. And again, it accounts for something like 35 to 40% of the total. And it's important to keep the ballast shoulders built up. And we measure the height of the ballast shoulders from the top of the sleeper and the width of the ballast shoulder laterally from the end of the sleeper. The final part is sleeper shoulder resistance, and this is the resistance on the sides of the sleeper derived from the pressure of the ballast upon it. Depends on the ballast profile in the cribs, the ballast density and its level of compaction, and the coefficient of friction between the ballast and the sleeper. And again, from a maintenance point of view, clearly the full shoulder resistance will not be achieved if the cribs are not full or they're not consolidated. Something perhaps new in the UK, but not so new on the continent, is the use of undersleeper pads. These two diagrams are taken from the PWI journal and from a paper presented at the Urban Rail Infrastructure Conference. The top diagram shows the contact area without undersleeper pads on the left and with undersleeper pads on the right. The contact area is increased from 2 to 8% up to 20 to 35%. And although not yet quantified, I believe this must have a beneficial effect on lateral resistance. The bottom diagram shows the effect on ballast pressure from the use of undersleeper pads, and clearly increasing the contact area will reduce the contact pressure and reduce the degradation of ballast, so they have important advantages from a maintenance point of view. So this diagram shows the typical influence of various track maintenance and renewal activities on lateral displacement. So the column on the left is the fully stabilized, so that's 100% resistance. So work that disturbs the ballast structure reduces lateral stability, and this is the reason why it is often necessary to impose speed restrictions after work. The use of the dynamic track stabilizer returns the lateral displacement resistance to a range where the track is protected against buckling, and it is practiced on the continent to use the DTS after maintenance tamping to avoid the need for critical rail temperature speeds. And indeed, Network Rail is actively working at the moment of making it easier to deploy DTS on maintenance sites. The lateral resistance to buckling increases after track work due to the load from the rail traffic and depending on the track structure. And lateral displacement is fully restored after between 0.5 and 3 million tonnes of traffic. And using a DTS corresponds to a traffic loading of at least 100,000 tonnes. So Network Rail Standard TRK 001 sets out the rules by which consolidation of the ballast and hence return of buckling resistance is calculated. But on many lightly used passenger-only routes, the passage of 3 million tonnes of traffic can take some time to accrue. Right, so let's have a look at some of the factors that influence, and this is extracted from Bernard Lichberger's book, looking at some of the factors. So what we've got here is a number of factors, which in the down the left-hand side, and whether they are very good, good, minor, poor, or very poor for lateral displacement resistance of the track. Remember, they might have different effects in terms of other maintenance. So if we look at box 1, so bigger, heavier sleepers are good, as they increase the resistance. And twin block sleepers are very good, but their application in the UK has been very limited, and I don't think is likely to extend at the present. And indeed, France and Belgium, who've traditionally used twin block sleepers, are now using monoblock sleepers themselves. So the second box there, making sure that the sleeper can achieve the maximum resistance in the ballast is good. So minimizing voiding and the use of lateral resistance plates where required to improve resistance is essential. Examples, we use them in tight curves, but they're also used to help resist track shifting forces in switches and things like that. So box 3 is maximizing the ballast. So this is things like increased ballast grain size and ballast shoulder height and things like that. So maximizing ballast resistance is good for the track. So maintaining the ballast profile, including the shoulder height and width, and keeping the cribs full is important. And don't forget the shoulder width, as I said, is measured from the end of the sleeper and the shoulder height from the top of the sleeper. The next box, again, looks at things like narrower sleeper spacing, improving the inertia, moment of inertia of the rails, and the torsional rigidity of the track grid. And we looked at those in the first part of the presentation. So closing up the sleeper spacing using stiffer rails are good for resistance. Yeah. And for example, British Railways on its most, or the UK Network Rail, on its heaviest used lines are now using the 1060 60 kilogram rail on the G44 concrete sleeper as standard. For anything that disturbs the track, ballast is poor or very poor for lateral resistance. So we need to plan when we're going to carry out these activities. And avoiding the potential periods when buckling is most likely. So things like track lifting, measured shovel packing, stone blowing and tamping must be done in a controlled way and precautions applied until the track has reconsolidated. The converse is also true, that things like dynamic track stabilization, that is very good, and heavy axle weight trains are good for consolidating the ballast. But train speeds themselves is not the big factor. It's the axle load that tends to be the deciding factor. And finally, temperature. Temperature alone is not a major influence, and it, in any event, is impossible to control. The temperature is what it's going to be, isn't it? So good inherent lateral track resistance to buckling is achieved by the measures described so far, and heat tends to be what causes problems. It's the straw that breaks the camel's back and reveals deficiencies in maintenance. Right, so let's have another think about another question. Why do we use stress-free temperature and not rail stress? So this is a plot of rail temperature against rail stress for CWR. So the slope of the line is a function of the properties of the rail and the rail steel. So things like coefficient of expansion, Young's modulus, cross-sectional shape, etc. And in the range we're talking about is a straight line. So the rail behaves elastically, and it's a straight line relationship. So when rail stress is positive, the rail is in tension, and there is a higher risk of broken rails. When the rail stress is negative, the rail is in compression, and this increases the risk of track buckling. The rail temperature at the intersection of the function, with the temperature axis is the stress-free temperature. And that is that the rail is at the length it would be if unconstrained at that temperature, and it is neither in tension nor compression. So if the rail were to be laid out and fastened down at whatever the ambient temperature was, the SFT would be this rail temperature, the stress-free temperature. And clearly this would vary a lot throughout the year, or indeed the time of day. However, it is a constant once the rail is fastened down, but the stress varies with rail temperature. So as the temperature goes up, the rail goes into compression. As the temperature goes down, the rail goes into tension. So we use stress-free temperature as a surrogate for rail stress because in practice we can't directly measure the actual stress in the rail. With the possible exception of the verse equipment, and even this is an intrusive inspection. But we can readily measure rail temperature. So by using a measure related to track rail temperature, we can readily monitor the state of the stress in the track, provided it's been set correctly beginningly. As discussed, the stress in the rail constantly changes with temperature, but the stress at SFT when the rail is at the length it would be if unconstrained is a constant once set. So the current practice in the UK is to stretch the rail to the length it would be at a rail temperature of 27 degrees by stretching it hydraulically. And the same result can be achieved by waiting for a time when the temperature is 27 degrees and then clipping it down, so-called natural stressing, or by heating the unconstrained rail with rail warmers until it is at 27 degrees, then clipping it down. So hydraulic tensors are the preferred method as the process can be accurately controlled. The stress in the rail is directly proportional to the stress-free temperature, and if the stress is plotted against the length of a long welded rail, that's the mileage along the bottom scale, a plot like this would be derived. So provided the stressing operation has been properly carried out, the body of the rail will have a constant stress, and that's from B to C. Yeah. At each free end, so an adjustment switch, for example, or indeed an end of the line, the rail stress is 0, and the slope of the stress transitions, A, B, and C, D, is proportional to the resistance of the rail fastenings. So that is how many fastenings and their sleepers are needed to prevent the rail moving. The slope will be shallow if low toe load fastenings are in use, for example, PR 401A clips, and steeper if high toe load fastenings are used, for example, fast clips in G44 sleepers. And it shouldn't confuse the stress transition with the anchor for stressing. This is what it settles down to after a time under traffic. So, effects of rail creep and installing a rail without stress restoration. So many track maintenance and renewal activities can change the stress in the rail and hence the stress-free temperature. So there are many activities that affect the stress-free temperature, including lateral and vertical movement of the track. But these diagrams show two common things that will change the SFT. So the top diagram shows the effect of rail creep. As the rail creeps from left to right, the rail stress increases where the rail is stretched out, but falls where the rail bunches up. So thinking of jointed track may help to visualize that. And the result is an increase in the stress-free temperature where it is stretched out, but a reduction in stress-free temperature and increased risk of buckling where the rail is bunched up. The bottom diagram shows the effect of replacing a rail without stress restoration. This causes a local loss of stress and SFT. And whilst a single event may be tolerable, the effect of multiple defect removal will have a detrimental effect over time. And this is why stress restoration following rail changing is really important. So what is the effect of low SFT? So this is the diagram from earlier, and as can be seen, the effect of the low stress-free temperature, which is the red line, means that the rail goes into compression at a much lower temperature, and hence the risk of buckling is increased, all other factors being the same. So let's think a little bit about jointed track as well and how it works. So this is a similar diagram for jointed track. The slope of the graph is the same as that for CWR, as it's a function of the properties of the rail. So, and most of the rail stills are similar from things like coefficient of expansion. In jointed track, the effect of the joints is to provide a working rail temperature range where nominally the stress in the rail is zero. It isn't actually zero because obviously there's quite a lot of internal friction in the system, but for the purposes of this exercise, we can assume it's zero. So for properly adjusted and maintained jointed track, when the rail temperature is below about 10 degrees C, then the joint is as wide as it can be, so about 12.5 millimeters or half an inch. And the bolts are tight against the holes in the fish plates and the rail, which is why you can't get the fish plates off in cold weather. Below 10 degrees, the rails and fish plates will start to go into tension, and there is an enhanced risk of fish plate failure. When the rail temperature reaches about 38 degrees, 100 degrees Fahrenheit in older money, the expansion gaps will have been entirely used up and the rail ends will come into contact. And any increase in the rail temperature above this will put the rail into compression and buckling risk increases. From this, we can see that for much of the year, the 12.5 millimeter movement is sufficient to accommodate the likely temperature range. I did say that properly adjusted and maintained jointed track is important. So this requires that the rail ends are correctly drilled, the correct fish plates for the rail type are used, the expansion gaps are correctly set to the temperature on the day when the rail's installed, the joints are properly lubricated because they must be able to move, and importantly, the fish bolts must not be over tightened. If the joints are locked up, the track will behave like CWR. And in general, jointed track does not have the lateral resistance to tolerate this. It's often lighter construction with low toe load fastenings and does not have the same ballast profile as CWR. Unlike the diagram for low SFT, this shows the effect of lack of expansion gaps. So this diagram shows, again, the red line, the loss of the expansion gaps. And the effect is that the working range is reduced, and the track has a low joint closing temperature as we describe it. With the expansion gaps closing at a much lower temperature, the track will go into compression sooner and the risk of buckling increases. So moving on from the theory side of it, let's have a look at some learning and from past buckles, and indeed some of the reasons that we've got the standards we've got today. So the buff bars are the numbers of buckles in jointed track. The bottom scale is years from 1958 to 1973, and it's a mileage of track up the left-hand side. So 1969 wasn't a great year. The mauve bars are the buckles in CWR track. The green line is the mileage of jointed track falling from nearly 34,000 miles in 1958 to 15,600 by 1973. And the blue line is the mileage of CWR track, rising from only 117 miles in 1958 to over 7,000 by 1973. And in 1969, they had 48 buckles against an average of less than 4 in the previous 11 years. This is CWR buckles. And 3 of those buckles led to high-speed derailments, and 2 of them of passenger trains. So we derailed an empty car flat train at Lichfield on the 10th of June on the West Coast Main Line. The Paignton to Paddington loco-hauled express train was derailed at nearly 80 miles an hour near Somerton, with 65 passengers injured. And the Tyne Tees Pullman, travelling at about 95 miles an hour, was derailed at Sandy on the East Coast Main Line, with 11 injured. So if you normalise this by track mileage, so it's normalised by buckles per 1,000 miles of track, it involves what the dramatic change this was. And as you can see, 1969 was not a good year for track buckling. In fact, it caused so much concern having these buckles in such a short space of time that questions were asked in the House of Commons, and the Her Majesty's Railway Inspectorate was directed to do a class review on the safety of CWR as part of the derailment investigations. Concurrently, BR started a review on its procedures for the managing of CWR and a major programme of remedial works across the network. That included adding a lot of extra ballast. The interim HMRI report was published in 1970, and BR published the revised Handbook 11 the same year. And that's the direct ancestor of 3011 we still use now. Final HMRI report was not published until 1974 to allow for the inclusion of experimental and test results. And the measures taken by BR include better procedures, making ballast profiles up to new standards, and restressing locations where the SFT was low proved successful, as we shall see. So what did the HMRI findings? So of these buckles, 17 of the 48, consolidation of the ballast was unsatisfactory and voiding was present below the sleepers. And we've seen the big impact that the ballast resistance around the sleepers has on lateral stability. 13 of the 48, the distortion could be attributed in whole or part to failure to carry out the provisions of Handbook 11 as it was then. So over a quarter of them were caused by not stressing the track properly. Of the remaining 18, 11 were associated with discontinuities of some form, such as CWR catch points, insulated joints and things like that. And the concern was that whilst the direct cause was established, the factor of safety against buckling was much lower than predicted by the then current methods of calculation. This needs to be considered in the light of some of the CWR having been installed to methods that were later found to be flawed, though were best considered good practice at the time. But also CWR is being installed on timber sleepers and with rail fastenings that would not today be considered suitable. However, there was clearly potential for change. This is another diagram from the report. So this is an extract from the HMRI report. So what we've got here is meteorological data for June to August 1969. And we've got plots of the maximum daytime temperature, the difference between the day and night temperatures, and the hours of sunshine. The buckles occurred in two concentrated periods between the 7th and 15th of June and 16th, the 7th and the 15th of June, and 16 between the 12th and the 16th of July. And all 48 occurred in the afternoon and early evening, and 83% between 1400 and 1800, of which 10 occurred between 1430 and 1530. I think that's all quite familiar. What was not really understood was what was going on in terms of temperatures. So the temperatures and hours of sunshine were not significantly higher than the previous years. And for example, they were lower than 1968. But during June and July 1969, there were many clear nights and early mornings when ground temperatures were low, and thus there was a large differential in temperatures between the overnight low and the afternoon peak. And this is now recognised as a significant factor and a significant risk in that period of the year, like now, where there was a frost last night, but this afternoon it's a beautiful warm afternoon. So what were the key changes that were made? So we moved from tensor stressing as the preferred method, and pulling using tensors to the equivalent length to an SFT of 27. The heater stressing was changed, range was changed from 18.3 to 27, so that's 65 to 80 Fahrenheit, to an acceptable range being 21 to 27, so that's 70 to 80 degrees Fahrenheit. More rigorous requirements to re-stress track where the SFT was outside the range were introduced. Better descriptions of how stressing was to be carried out, so addressing the problem of inconsistency in application. It introduced limitations of work to be undertaken in hot weather. So what you were not allowed to do in terms of disturbing the track when the weather was warm, things like tamping or opening out for sleeper changing. And it also prescribed for the first time some action to be taken when CWR was disturbed. So that's hot weather precautions, as we would now describe them. And the key requirements in the standards come from this original 1970 edition of Pattern Book 11. So the results were successful, as you can see. So the changes described were successful as the track buckles per 1,000 miles for CWR fell back to low levels and below jointed track for the first time, despite the increasing mileage of CWR track. I think it's perhaps interesting to reflect that from 1965 to 1973, CWR was being installed at an average of 580 miles a year, and had become, in my experience, the standard track for use everywhere. I came in 1973. At this rate, the jointed track would have soon gone, and this is perhaps one of the roots of the problems that the long interest in long-term maintenance of jointed track started to fade as those skilled in this left the industry and in the retrenchments that followed. So let's look at a few examples now. This was when I did this report. These are some of the buckles that we've had in recent times. And our last track buckle that led to a derailment was at Langworth on the 30th of June 2017. And we'll talk some more about that in a minute. But let's have a look at some examples because I want to pick out some common threads. So the first one we want to look at is Tatton Hall Junction. That's on the CNH3. That's the Crewe north to Holyhead route along the North Wales coast, and this happened in July 1971. So the buckle happened at 1808 when the temperature was estimated to be in excess of 38 degrees and the train was doing 68 miles an hour at the time of the derailment. The track was laid in 1958 with 109-pound wales on BR1 base plates with softwood sleepers at 24 to the length. The fish plates had been lubricated. The rail was creeping towards the S&C at Tattenhall Junction in the direction of traffic, but no rail anchors were fitted despite it being a known rail creep site. And some joints had crept to the extent that they were over the base plates. Investigation after the buckle found that 22 of the joints preceding the derailment, only 7 in the cess rail and 2 in the 6-foot rail, were not butted up solidly, and the joints were still butted up solidly at midnight when examined. The creep had first become of concern in February 1971, and they quite correctly planned for pulling back the rails in May 1971, but that wasn't completed. And unfortunately, they never came back to actually do it before the derailment. And to compound the issue, the site was disturbed by lifting and packing the joints following a track recording run on the 22nd and 23rd of June. So that's 9 days before the buckle, and no hot weather precautions were in place on the day. The picture shows the aftermath of the buckle and how the train had actually come into contact with the bridge, resulting in 2 fatalities and 26 injuries. So let's think about Huddlesford now. In July 2003, a lot of Guinness was spilt on the West Coast Main Line that day. So the track buckle happened at 16:38 on a very hot and sunny day when the temperature was estimated to be in the region of 40 degrees C. The train was doing about 75 miles an hour at the time of the derailment. The driver saw nothing of the buckle. The first the driver knew about it was when he got an emergency brake application. The track was newly laid with 1060 rail on G44 concrete sleepers, with NR1 base plates on the bridge in the foreground in the bottom picture. Reballasting had been carried out beyond the bridge using the medium output ballast cleaner. The track had been stressed to 27 degrees, but indications were that subsequent work to remove defective welds near the bridge had potentially lowered the SFT at the underbridge. The shoulder ballast profile over underbridge 95 and immediately south was deficient, and you can see from the photograph that the construction of the bridge doesn't allow you to build a properly heaped shoulder there. There were voids of the order of 4 to 6 millimeters below the sleepers immediately south of underbridge 95, which is where the buckle occurred. And there was poor vertical track geometry and cross level variation over the underbridge and immediately to the south at the site of the run-in to the recent ballast cleaning work. This was compounded by a lack of clarity with regard to the project maintenance strategy and led to, and this was the days of contractor maintenance and contractor renewal, and it led to inaction with regard to intervening to fix these deficiencies. Okay. Of importance then is that the report concluded the lateral misalignment was a heat-induced buckle and resulted from a probable low stress-free temperature and a combination of individual track features. Each of the track features in isolation was unlikely to be sufficient to trigger a buckle, which comes back to the point I was making in the theory part, that you've got to think of it as a system, and any one deficiency is probably not going to cause a buckle, but a combination of things, low ballast, voiding, and that can actually lead to these problems. Finally, let's have a look at Langworth. So the buckle happened at 14:15 when the temperature was estimated to be in excess of 38 degrees and was the hottest day of the year at the time of the buckle. Remember what I was saying about big differentials making a difference. The train was doing 46 miles an hour at the time. So 102A points were 113A rail on vertical on timbers, and 101B crossover was vertical on concrete, and the 14-metre panel between the 102A and 101B points was 113-pound rail on F27 sleepers. The records indicated the site was stressed to 27 degrees. It was known that the ballast profile was deficient That had been reported in March 2015. But remedial work in the ellipse had been reprioritised by the section manager. There was a long-standing misalignment at the toe of 101B points, which is where the buckle occurred, confirmed by records going back to June 2009. So there was plenty of opportunity to get in and fix the alignment problem. The eighth contained in the S&C was in the poor band for track quality, and the TRV traces indicated poor alignment at the S&C. There had been maintenance interventions, so they changed the crossing and had an IIJ changed. They could have adversely affected the stress-free temperature, but no records were made changes to the system, so nobody knew what effect they had. No hot weather precautions were in place on the day, and it is possible that a watchman, had they been present, may have reacted to the incipient buckle, which was seen by the train driver. And the picture shows the aftermath. So we're nearly at the end now, so let's think about some common threads. So the key for maintaining lateral resistance in CWR track is managing the stress-free temperature, because you can't see it. That's the problem. So you need to have robust processes and good record keeping to actually manage that. And it's all about managing the ballast profile. So cribs full, shoulders built up, lateral resistance plates fitted where needed, etc., etc. The key for maintaining lateral resistance in jointed track is managing the expansion gaps, and they're the equivalent of managing the SFT. And you've also got to make sure that the joints can move. So good lubrication, and don't over tighten the bolts, and make sure the rail ends are drilled correctly. And in all cases, we need to control rail creep, we need to control disturbance of the ballast, and we need to act on deficiencies in a timely way. And if we're not sure, then apply the necessary hot weather precautions. So I'll stress that, as we've seen, track buckles are not caused just by hot weather. Neither are they caused by deficiencies in a single area, and the track needs to be thought of as a system where each component has a part to play in maintaining the lateral resistance. So be conscious of deficiencies that will reduce the lateral stability and the impact that these will have when combined with the seasonal weather, and to take action to correct them before they are likely to become critical. And if you can't correct the deficiencies, then again, make sure the necessary precautions are applied. So I shall leave you to read this final thoughts. This is an extract from the report into a derailment at St Clears in South Wales in July 1975. Right, and that's me finished. Thank you. So I shall hand over to, I'm happy to take some questions now, Phil.
Yeah. We've got a couple coming up on the screen, Andy. So
okay,
we'll just run through them.
If I stop sharing, it might be easier. So.
Yeah, just let me know when you're ready and I'll fire away.
Well, you carry on.
Right. Is any study on the effect of the sleeper shape on track buckling, for example, a winged frame or ladder sleeper?
Yes, there are studies on that. The various countries have done work on that, and you can dramatically improve resistance, for instance, by having sleepers. The K sleepers are used in Germany, which have a diagonal bracing, makes the track much stiffer. The downside of them is it's not easy to maintain the track. It's not easy to slew the track when you've got those in place. So, but yes, various things have been looked at over the years, and it's I guess a toss-up between a simple to make sleeper, which we can use, as against a more complex structure, which needs possibly more maintenance work. So.
Okay. Next one from Sankadev. My question is regarding finding SFT in a country with no prior railway history. In the absence of annual rail temperature records, we had to resort to construct a dummy railway line, which is cost intensive. Is there any widely accepted theoretical method to find the stress-free temperature in such a case, i.e. deriving the rail temperature from the ambient air temperature?
Well, as a rule of thumb, we say that the rail temperature is about 1.5 times the ambient temperature. But that relationship tends to hold well when the weather's bright and sunny. Not so if you've got other conditions. So, I mean, to be quite honest, probably your best way to do it is to actually just some rail, just get some rail and actually try it out. So to record the temperature through the seasons and find out what's happening. But for instance, you'll get much higher rail temperatures in a place where you get, like today, a hot sunny day with direct sunlight, than you would on a hot day which was overcast and cloudy. Yeah, and things like rain and things like that, or mist can make a huge difference, and wind. So.
Okay, a question from somebody called Phil Kirkland. Mechanized shoulder compaction was undertaken in the late 70s and 80s, but it's not referenced on your slide number 16. Has this process now been totally discounted?
I think DTSing works better. Shoulder compaction, to do good shoulder compaction, you need a good ballast profile. And I think that's why it fell out of favour in the UK. You need to profile your ballast profile. But now the current sort of trends, the new machines, the track finishers, as they're now called, are ballast regulators, and they tend to be fitted with DTS now. So they regulate in brush, but they also consolidate the track using a DTS, which consolidates the ballast completely around the sleeper rather than just on the shoulders.
Okay. A note from Andrew Wilson. Thanks for the presentation. You didn't touch on painting the rails with white solar reflective coatings. What is your opinion of this process for controlling a buckle?
You can't rely on it as a means of controlling a buckle, but it certainly does suppress the rail temperature. So we did some experiments with it, and I think you can get probably 6 degrees or something out of it. What we did also find is the effect fades very quickly as it gets dirty, so you need to regularly redo it. Yeah. And obviously it doesn't have the same effect when the air temperature is quite high, the ambient temperature is quite high, but it does work quite well against strong solar radiation. So we've tended to use it mainly in places like S&C, where we want to stop switch toe movements in switch diamonds and things like that. Other countries have done it. The Italians spray their CWR with whitewash on an annual basis, again to keep it fresh, and because that's a very quick and easy way to do it. Yeah, but you do need to also be careful about rail inspection as well. So for instance, you wouldn't want to paint anything that you need to rely on good visual inspection for cracks, for example, in cast crossings.
Yeah. Okay, next one from Keith Nichols. Where voids are reported to be associated with buckles, do we know they were there prior to the incident? Granular materials can dilate when sheared. Is it possible the voids were caused by the buckle?
After the, it depends on the buckle, but yes, I think we can fairly safely say that the voiding is there by looking at the track away from the immediate site of the buckle. You can use void meters and we can test for voiding. Obviously, where the track has actually buckled, yes, you've lost that. That's information will have gone because it's been too disturbed. But yeah, we can do, and it is definitely a factor. It's also a factor if you see that a lot of buckles are associated with things like wet beds, which aren't actually, if you get bad wet beds, they dry up in the summer and you get lots of voiding from that, and that's a common cause of triggers for buckling.
Yeah, often, as you say, there's strong signs of attrition around the the approach, isn't there? Andrew Wilson, what about steel sleepers? They have more surface area contacting the ballast and bigger spade ends to improve lateral resistance. Do you see many buckles on steel sleeper track?
Not on spade-ended steel sleepers. The McDonald end, the crimped end steel sleepers buckle if the sun even comes out, let alone. So they are very, very poor. The spade-ended ones are generally as good as concrete sleepers. Yeah, so we do see the odd one, but
yeah, I have seen steel sleepers lift vertically as a panel because of the compressive force.
Yeah, and they are obviously much lighter as well. Yeah, so.
One from
typically these days, most of the track buckles occur, the majority, in old jointed track or in vertical S&C. So.
Yeah. Next one from Fabian Hansman. How do you think climate change will affect the risk of track buckling?
This is always a good. I mean, clearly, if we are going to get more hotter days, I think the first impact is going to be we'll see a lot more hot weather precautions applied. So we'll have more days when we have speed restrictions and things on because the rail temperature's triggered action. So we can counteract that by managing things like the ballast a lot better. Network Rail has done some research looking at the effects of, I mean, should we be increasing the stress-free temperature, for example? And I don't think there's a strong case to do that yet. But it's about managing the track in a more robust way to avoid the hot weather precautions in hot weather. So, on the hot days, you don't have to put the speeds on if the track's in good condition and consolidated. So that may see perhaps further restrictions on when we are allowed to do tamping and things like that, to avoid, working during the hottest period of the year. But at the moment, we want to use the plant all the year round, so it's not really a way we particularly want to go.
Okay, it's time's moving on. It's 13:30. I'll do the one last question from Mark Holderness. He's working out in the UAE and the stress-free temperature is 40+ degrees.
Yep.
His concern is that the ballast profile shoulders should be higher and wider than the UK. Would you have any suggestions?
I would anticipate them probably needing to be higher and wider. Yeah. Again, there's quite a lot of theoretical research about that. The question I would ask is, what's your minimum rail temperatures? So obviously, if you go for a very high SFT, which is good news for buckling, the problem is if you get cold temperatures at night, and I know the Canadians suffer problems with this and other places in North America, where during the winter, the prolonged cold weather causes the track radius to reduce. It pulls in on the curves, and they have to do quite a lot of remedial work in the spring to actually put the track back where it was. So I think it's about not just the top temperature, it's about keeping an eye on what the minimum temperatures are going to be as well. But yeah, to stop track shifting, a very cost-effective way of doing it, either close up the number of sleepers is a good start, and also add a wider, deeper shoulder. Yeah,
we had similar events in northwestern Australia. We had very high daytime temperatures in the desert, but even in the summer it would get down below 0 during the night. So even with a 136-pound rail, we would get quite a few rail breaks during the day, during the night. So yeah. Okay, right. Time's up. So we had at one point 93 participants, so well done everybody. Thanks for attending, and please pass the message on to your colleagues. These are really interesting events. And a big thank you to Andy for giving up his time and
his
putting
lunch.
together his lunch. Yeah. Well, you don't get a lunch on the railway, do you? But thanks, Andy, for all the effort you've put into a splendid presentation. If we can all just say thanks to Andy, and I'll end the presentation now. Thank you.
Thanks.